Hello. This podcast is about describing motion with position time graphs. First, we'll learn how to create a position time graph, then we'll learn how to interpret motions represented by the shape of the position time graph. As the name implies, to create a position time graph, we need time and position data. So here's our data. We need to create our graph. The y-axis represents position. The x-axis represents time. Because position is a vector quantity, we can have negative quantities as well as positive quantities, because remember, in physics, the plus and minus sign have nothing to do with the value of the vector quantity, but everything to do with the direction of the vector quantity. So because we have negative values, our timeline is actually in the middle of the graph. We're used to seeing the x-axis down at the bottom, but here it's in the middle. Now we want to go ahead and plot our first point, and that is 0, 0. Notice for the first 4 seconds the object doesn't move, so our two additional points are going to be on the time axis, and we notice that when an object's at rest, we're going to get a flat line, also known as a horizontal line, on our position time graph. Now, beginning at second 4, we can see that the object starts to move, and at 6 seconds, it is at position 4 meters. And we'll go ahead and plot our next few points. And we notice that from 4 seconds to 10 seconds, the object is moving in the positive direction from 0 meters to 12 meters. We've plotted those points. And now notice as we move to 12 seconds, it is changing directions and moving back towards the origin. But before we plot those points, let's notice that when we have a rightward motion, the line is going to go up and to the right. Let's plot the rest of our data points. Notice that when we have an object moving leftward, the line is going to be down and to the right. Now that we've learned how to create a position time graph, let's go ahead and learn about interpreting it. Here's a position time graph representing the motion of an object, and we're going to go ahead and break this down and learn how to interpret the shape of the lines as well as the position of the lines and what it means in terms of motion. Two important things to keep in mind as we're interpreting a position time graph. The y-axis represents motion, so if you have a change in the y-coordinate, it represents a change in the object's position. And the x-axis represents time, so if you have a change in the x-coordinate, it represents a change in time. And of course, time always moves forward, so we're always going to have a change in the x-coordinate. But as we've seen before, we won't always have a change in the y-coordinate. So let's go ahead and break this down in a systematic way. First, let's look at the object's position, in other words, its location relative to the origin. And if the object is to the right of the origin, we're going to find the position timeline above the time axis in this region. If the object's position is to the left of the origin, then we're going to find the position timeline below the time axis in this region. Let's take a look at the object's direction of motion and how we interpret that. And now I'm going to bring up different segments of that position time graph, and they're not going to be brought up in chronological order. If we have no motion, we're going to get a flat line, as we see here. And let's just take a closer look at why a flat line is going to be created. Keep in mind that the y-axis represents position, so if we have no change in motion, we're going to have no change in the y-coordinate, and that creates a flat or horizontal line. Next, rightward motion creates a line up and to the right, or a positive slope, as we have in these two areas. And the reason for that is, again, if we're moving in the positive direction, we're going to have a change in our y-coordinate, and it's going to be a change away from the time axis in the upward direction. So rightward motion is a line going up and to the right. Conversely, leftward motion is going to create a line that's down and to the right, as we see here. And again, that's because if we're moving downward on the y-axis, if we have a change in the y-coordinate, that means that we're moving to the left. Notice you can be moving leftward and still be right of the origin. just like you can be left of the origin and moving rightward. So let's just take a look at this blue line. Here, we're to the right of the origin and we're heading back towards the origin. Here we've reached the origin and we're continuing to move leftward and away from the origin. Finally, let's look at how we use the shape of the position timelines to interpret the object's speed. The object's speed is going to show up in the slope of these position timelines. And let's take a closer look at why that is. As we remember from math class, the slope is a measure of how the y-coordinate changes as the x-coordinate changes. Or we often learned it as the rise over the run. In this graph, the rise represents the change in position and the run represents the time. We know when an object's moving faster, it's going to have a greater change in position for the same amount of time, and that's going to give us a steeper slope. When an object is moving slower, it's going to have a smaller change in position for the same amount of time, and that's going to give us a flatter slope. If an object has no change in position at all, it's not going to have any rise, and that means it's going to have a slope of 0. We can sum this up. No speed or being at rest creates a 0 slope, as we see here with the two red sections. Slower speeds create a flatter slope, and faster speeds create a steeper slope. Let's use that information to rank the speed of the remaining 3 sections. And so we want to look at the slope, and we can see that this section here has the flattest slope. So we're going to go ahead and call that moving. We notice that this has the steepest slope, and this slope is in the middle. So we can rank them as this is faster motion than this section. And during this section, we have the fastest motion. Notice the direction of the line down and to the right or up and to the left doesn't have anything to do with the speed. You can have a negative slope with a faster speed than a positive slope, because in physics, the plus and minus sign have nothing to do with the value of the quantity. It has everything to do with the direction. When we're judging or ranking speed, or which one's going the fastest, we're looking for the steepest slope. Doesn't matter if it's a negative slope or a positive slope. Now that we've learned the fundamentals of creating and interpreting position time graphs, let's look at some of the differences between constant velocity and accelerated motion. Here is the position time graph for the dune buggy and the fan cart that we saw in the first podcast. This is the first segment when the fan cart was speeding up. The dune buggy is in green dots and the fan cart is in red dots. Notice the dune buggy has a straight line as a position time graph, which we know that from our previous unit on constant velocity. However, the fan cart's position time graph is not a straight line. It's a curve. And that's because the displacement every half second is getting larger and larger. And when that displacement gets larger and larger, it bends the line and creates a curve. Now, the velocity of the object is simply the slope of the position timeline. Now, when it's constant velocity, we have a straight line and the slope is the same the whole way, which means the speed doesn't change. However, we know with speeding up that the speed's going to get larger and larger, and that shows in the curve as the slope is going to get steeper and steeper. Notice that the curve starts out flat and it keeps getting steeper and steeper. That means the object is getting faster and faster. And we can turn on our tangent line function. And this is just a neat function that we can put over each data point. So here you can see the tangent lines for the dune buggy and for the fan cart. And up here you can see the slope. So the dune buggy is going faster. It has a slope of 0.449 meters per second. The fan cart, only 0.251 meters per second. Now, if we go to the next data point, you can see that the dune buggy's slope is the same, but the fan cart slope has increased to 0.35. When we go to the next data point, Now the fan cart is going a little bit faster than the dune buggy, 0.493, whereas the slope the dune buggy is basically the same, 0.44. If we move on to the next time data point, you can see the fan cart slope is getting even steeper, 0.644, whereas the dune buggy's slope is remaining essentially the same, 0.433. If we move on to the next data point, the fan cart's velocity has increased to 0.767 meters per second, and at 1 second, the fan cart's velocity has increased to 0.842 meters per second. So let's take a look at what this position time graph looks like for slowing down. Okay, when the when the fan cart was slowing down, here's our position time graph. We can see that the dune buggy in green here is a straight line. That means constant velocity. The displacement every half second is the same. However, with the fan cart, we know that the displacement is getting less and less as time goes on, and that acts to flatten out the line or bend the line down, creating a curve. Now this curve, notice, this curve goes from steeper to flatter. That's different than our speeding up curve, which went from flatter to steeper. And so when you have a curve that goes from steeper to flatter, remember the steepness is an indication of the speed. Well, if it starts out steep, that means it's starting out fast, and if it gets flatter, that means it's getting slower. So this shape, where it flattens out as time goes on, is a position time graph for an object that's slowing down. And we can just go ahead and use our tangent function and take a look at this. So we can see initially the fan cart was going much faster than the dune buggy, 0.722 meters per second versus 0.414 meters per second. If we go to the next data point, fan cart slowed down to 0.642. In our next data point, the fan cart slowed down to 0.526. When we go to the next time point, it slowed down to 0.402. And when we get to the next time data point, it slowed down to 0.295, and it is now going slower than the dune buggy. And at our last data point, it slowed down even more to 0.225 meters per second. So again, this is a position time graph for an object that's slowing down. It's a curve, just like the object that's speeding up, but the curve goes from steeper to flatter, whereas when it's speeding up, it goes from flatter to steeper. Well, that wraps up this lesson. Let's review what we learned. First, movement is represented by changes in the y-coordinate, and time is represented by changes in the x-coordinate. When it comes to interpreting the position time graph, the shape describes the object's motion. A flat line means there is no motion, a straight line means constant velocity motion, and a curve means accelerated motion. That could be either speeding up or slowing down. In terms of position, if it's above the time axis, then we know the object's to the right of the origin. If the position timeline is below the time axis, then we know the object is to the left of the origin. When it comes to direction, a line that's moving up and to the right, in other words a positive slope, indicates the object's moving rightward, and conversely a line moving down and to the right, which we know is a negative slope, indicates that the object is moving leftward. Finally, when it comes to speed, the slope determines the speed, and we know that a steeper slope, either positive or negative, represents faster speed. Well, this ends our podcast. I hope this has helped, and have a good day.